Hello everyone, welcome you all. I am Professor Awais Ahmed Hussaini, working as Assistant Professor in Mechanical Engineering Department at Sharad Institute of Technology, College of Engineering, Yadra. In this video, we will discuss how to solve the numericals related with the steam condenser. So as we know that the main function of the steam condenser is to convert the steam into condensate, that is water. In theoretical part, we also discussed so many types of the steam condenser, and the particular steam condenser are mostly divided into two types. One is jet condenser and second one is surface condenser. So main specialty of condenser in case of the steam power plant is to improve the performance of that overall steam power plant. And the main function of that steam condenser is to keep the pressure lower after expansion process in the turbine, also to convert that steam to water and supply that condensate, that is water, again to the boiler through the different feed pumps with the help of that hot well arrangement. So here we will discuss some basic fundamentals about that steam condenser before starting the numericals. So the most important parameter while solving the numerical in case of the steam condenser, or you can say it as the most important formula, is based on that Dalton's law of partial pressure. So you must have to know what is exactly that Dalton's law of partial pressure. So it states that the pressure of the mixture of air and steam is equal to the sum of pressure which each constituent would exert if it occupied the same space by itself. I repeat once again, the pressure of the mixture, it includes that air and steam, is equal to sum of pressure which each constituent would exert if it occupied the same space by itself. So mathematically it can be right, PC is equal to PA plus PS. So here this is the most important formula of the Dalton's law of the partial pressure, that is PC is equal to PA plus PS, where PA stands for partial pressure of the air and PS stand for partial pressure of the steam. Now by just a rearrangement, here you will get the main formula of the Dalton's law of partial pressure, that is PA is equal to PC minus PS. So in each and every problem of the steam condenser, it starts with this particular formula of PC and PA. So we must have to know that PC is equal to PA plus PS according to the definition, and just by simple mathematical calculation or rearrangement of the terms, PA is equal to PC minus PS. So this is the most important formula while solving the numericals related with the steam condenser. Now let us start with the first simple numerical based on steam condenser. So the numerical is: the following observations were recorded during a condenser test. The following observations were recorded during the condenser test. First is vacuum reading. Vacuum reading is given in the numerical. It is around 700 mm of Hg. And second one is barometric reading. It is around 760 mm of Hg. And students, keep in mind that in numerical, if suppose that barometric reading is not given, you can assume it as 760 mm of Hg. It is a standard value. And the next is condensate temperature. So condensate temperature is given in the numerical. It is around 34 degree Celsius. So we have to find the partial pressure of the air, that is PA, we have to calculate. And second one is mass of the air per meter cube of the condenser volume. Here again one parameter is hidden, but it is mentioned, that is per meter cube. Means here you can take volume is equal to 1 meter cube. Now these are the given terms in the numerical. First is vacuum reading is already given in the numerical. It is around 700 mm of Hg. And second one is barometric reading. It is around 760 mm of Hg. Students, keep in mind that the unit of, while solving the numerical, you must have to focus on the units. The unit of that vacuum as well as barometric reading must be same. Here it is same, no doubt. Now the temperature of that condensate is given. It is around 34 degrees centigrade. You just convert it into Kelvin by adding 273. Here you will get the temperature. Now first parameter we have to calculate is partial pressure of the air, that is PA. Now there is one standard formula of that particular PC is, so here is a PC. First we must have to calculate the formula of the PC. So that PC include barometric reading minus vacuum reading. So whatever value of the PC is come, you can put in this particular formula. So there is one separate formula of that condenser pressure, that is PC. So the PC is equal to barometric reading minus vacuum reading. Here the unit of that vacuum reading and barometric reading both are same, so there is no need of any kind of the conversion. So here I just put the value of the barometric reading, it is around 760, and I just put the value of the vacuum reading, it is around 700. So after subtracting you will get the answer, that is 60 mm of Hg. So this is all about the value of the PC. Now in order to calculate or in order to convert it into bar, you just multiply it by the conversion factor, that is 0.00133. So this is the multiplication factor. It is required to convert that mm of Hg into bar. So here you will get idea 1 mm of Hg is equal to 0.00133 bar. If you want to convert one term from mm of Hg into bar, then you have to multiply it by that 0.00133. So here you will get answer in bar. So both answers are right. One is mm of Hg and another is in bar. But for further calculation we need answer in bars. So that's why we just convert that particular unit from mm of Hg into bar. Okay, so here we get the value of the PC. It is around 0.0798 bar. Now in the problem what temperature is given, that is condensate temperature. It is around 34 degrees centigrade. So from steam table corresponding to 34 degree centigrade, we just have to calculate that value of PS. Okay, so the value of PS is around 0.0532 bar. Okay, so from steam table corresponding to temperature 34 degree centigrade, we calculated value of the PS. It is around 0.0532 bar. So here is the one screenshot of that particular steam table which include the temperature 34 degree centigrade. So the adjacent value of that temperature column is a pressure. So here we get that particular pressure. So for corresponding to that 34 degree temperature, the value of pressure is 0.05318 bar. So that pressure is in bar. So that's why we just convert that earlier value of the PC into bar in order to keep the same unit. So now here once we get that PS from that steam table, we just put that all values in that standard formula of that PA. So what is the standard formula of the PA? PA is equal to PC minus PS. PA is equal to PC minus PS. Here the value of the PS from the steam table is coming from the bar. It is the unit is bar. So that's why we just convert that PC unit from the mm of Hg into bar. So after putting all values, both entities are in bar, you get, after subtracting, you get the answer in bar. So this is PA, it is around 0.0266 bar. So here we get the first parameter. Now our second parameter for calculation, and it is mentioned in the numerical, is mass of the air. Similar way, the volume is given, that is here that particular word mentioned per meter cube of condenser volume. So here you can take volume is equal to 1 and we have to find out the mass. So the next step is we have to apply the formula of MA. So this is a very standard equation, standard formula you already studied in second year in basic thermodynamics in case of that generalized gas equation part, that is PV is equal to MRT. So after using that particular formula PV is equal to MRT, the unknown parameter we have to calculate is MA. So that PA is available with us, we just put that value of the PA here. PA is calculated here. So this is PA. Now but the most important thing is the PA is available in bar. We have to convert it into Newton per meter square. So you have to multiply that bar into 10 raised to 5. So we get that particular answer in Newton per meter square. Okay. So here 0.0266 into 10 raised to 5 into 1. 1 is nothing but the value of the volume. Here, so students, here the value of R, that is constant, it is around 287 in joule per kg Kelvin. Now we have to take temperature in Kelvin. So 34 degree plus 273, we get the answer, it is around 307 Kelvin. And final answer of that MA is 0.03 kg. So here we get the answer. So once again I repeat that particular part. In order to calculate the mass, we are using the generalized gas equation, that is PV is equal to MRT. In that, unknown parameter is only one, that is MA. So just we reshuffle the terms and the formula is MA is equal to PA V upon R into T, where PA is nothing but the air pressure, Dalton's law of the partial pressure, V stand for the volume, R stand for that constant, gas constant, and T is nothing but the temperature. So we must have to take that P in Newton per meter square. Volume should be in meter cube. That R value should be in joule per kg Kelvin. If it is not mentioned in the problem, you directly take it as 287 because it is a standard. And you always take temperature in Kelvin. After putting all values, you get that particular term of MA. So in this way, it is very easy to calculate the value of the PA and MA with the help of that steam table as well. So this is all about first numerical. Now also we need some important formula in order to calculate the next numerical. So the next step of the solving the numerical, the one formula is included in that particular case is that particular corrected vacuum. So in some numericals it may be asked to calculate that corrected vacuum. The formula of that corrected vacuum is 760 minus PC. So this is a PC, you know, that is barometric reading minus vacuum reading is nothing but what? PC. So that 760 minus PC is nothing but corrected vacuum. Okay. So on the basis of that, we will take that simple numerical. So a vacuum gauge fitted to a condenser read, it is around 680 mm of Hg when the barometric read is 750 mm of Hg. Here the value of the barometric read get changed from 760, but you can take as it is 750. Determine the corrected vacuum. We have to find the corrected vacuum in both unit, that is in mm of Hg, also in bar. So in this particular problem, the given parameters are vacuum gauge reading, it is around 680 mm of Hg, and barometric reading it is around 750 mm of Hg. So first we have to calculate the value of the PC. How we calculate? That PC is nothing but barometric reading minus vacuum reading. So after putting those values, we get the answer, that is 70 in mm of Hg. Okay. So now in order to calculate that corrected vacuum, the formula of that corrected vacuum is 760 minus PC. So according to that formula, I just wrote here that 760 minus 70. That 70 is nothing but the value of the PC, which is coming from by using formula barometric reading minus vacuum reading. So here we get that corrected vacuum in mm of Hg. So in numerical, they asked to calculate that corrected vacuum by using both method or both way. In one is that mm of Hg and second one is bar. So in order to calculate or that particular term in bar, you just have to convert that unit from mm of Hg to bar by multiplying it by conversion factor 0.00133. So that's 690 into 0.00133. Here we get the answer, that is 0.918 bar. So this is the way through which we can solve the simple numericals related with that particular steam condenser. Okay. So one more important thing in case of the steam condenser is the efficiency formula. So the most important third formula is vacuum efficiency. So that vacuum efficiency is nothing but simply the ratio of actual vacuum upon ideal vacuum. So student, this is the most important formula. Okay, in examination always there is a one numerical will asked on the basis of the efficiency related to the steam condenser. You must have to know that particular formula of the vacuum efficiency. So the formula of the vacuum efficiency is, it is the ratio of actual vacuum to the ideal vacuum, where actual vacuum is nothing but barometric reading minus actual reading, or you can say it as actual vacuum is equal to barometric pressure minus actual pressure, and second one is ideal vacuum. In order to calculate that ideal vacuum, we must have to use one formula, that is ideal vacuum is equal to barometric pressure minus ideal pressure. So these are the important formulae related with that efficiency. But one shortcut I will tell you here. You always keep it in your mind. There is no need of the calculation of that actual vacuum, because it is already given in the numerical. So that value of actual vacuum is always related with the one particular parameter of that vacuum reading. So vacuum reading is nothing but actual vacuum. So there is no need of the use of this particular formula of the actual vacuum in order to solve the numericals. In numerical always they are given two parameters. Out of them one is actual, that is a particular barometric reading, and second one is vacuum reading. So that vacuum reading is nothing but that actual vacuum. So that particular value of the numerator is directly given in the numerical. So there is no any kind of the calculation is required. But we have to find that ideal vacuum by using that particular formula. Ideal vacuum is equal to barometric pressure minus ideal pressure. Barometric pressure is also given in the numerical, but we have to calculate that ideal pressure from steam table. And in order to calculate that ideal pressure, in the problem they are given some kind of the temperature. On the basis of temperature, we can calculate the ideal pressure. So students, this is all about some fundamental terms related with the numericals of the steam condenser. In next video, again we will discuss few numericals based on that vacuum efficiency, that Dalton's law of the partial pressure, then the mass of the air. Thank you.